In the last lecture, we had discussed some aspects of the colliders and accelerators and colliders. Here, we will actually consider what is called the other part of the scattering experiment, which is a detector. First, we will look at the basics of the detectors. Essentially, what one need to know is what are the energies and the positions of the particles, final particles, the particles of the products of the collision or scattering. And from these, we will be able to derive information about the dynamics at the interaction of these particles. So, that is the idea. So, as I mentioned in the previous lecture, new particles can be created, right, and these new particles can have the type of the particle, like what is the charge of the particle, what is the mass of the particle, etc., are also valuable information apart from the energy and the position of these particles, etc. So, in principle, a detector is a device that can indicate the presence of a particle, absorb energy and therefore give information about the energy of the particle, and then tell from the position of the detector, position of this thing, where the particle is detected. Okay. Our eye is a detector, it detects the photons coming from various objects around us, okay, light scattered from the table, okay, for example, from the computer. All this falls in our eyes, and then we reconstruct, our brain reconstructs this image and then tells us that this is a computer, or this is a table, or this is the letter that we are reading, etc. Similar to that, all this information that the detectors, various different parts of the detectors collect, can be fed to a central system, computers, and that can actually reconstruct the whole thing as much as possible with this thing. And this is made possible, like this absorption of the particle is made possible by the interaction of these particles. The particles interact with the matter, interact with the material of the detector. We will quickly go through some very basic type of detectors, basics of elementary detectors that are used even today. Okay. One is called the proportional counter. So, this is a simple idea. You have a cylindrical tube, okay, that acts as a cathode with a negative potential, electric potential, compared to an anode passing along the axis. See. So, this is your anode, and this is an anode, and this is the cylinder itself is your cathode. So, inside this tube there is an electrostatic field, electric potential difference and electrostatic field, which will be useful in detecting the particle. How is it done? Imagine a charged particle pass through this one. This tube will be filled with some appropriately used gas, and this gas will ionize as the particle, charged particle with high energy pass through this thing. Okay, it will say knock out the electrons from the molecules of the atoms of the material inside or the gas inside this thing. So, let us say an electron is produced by the interaction of this, and it is ejected from this thing. Once the electron is ejected from the atom, because of the electric potential between the cathode and potential difference between the cathode and the anode, the electrons will will be accelerated slowly towards the anode, and as it goes up, it picks up energy, high energy, and then basically as the energy of the electron is increased, it will have enough energy to knock out other electrons or electrons from other molecules or other atoms of the material inside. So, what happens is that it slowly goes, and then as it gets sufficiently large energy, there is an avalanche, suddenly there is an avalanche of avalanche happens, and then there will be a shower of these electrons, electron ion produced, and then there will be a lot of these electrons near the anode, produced near the anode and absorbed by the anodes. So, this is one of the basic type of detectors which are called proportional counters. Okay. And as I said, the primary electrons produced are accelerated towards the anode and gains energy and eventually causes an avalanche. And basically, this number of electrons, secondary electrons which are produced in the avalanche is proportional to the number of primary electrons produced. That is why it is called a proportional counter. Typically, the voltage between the anode and the cathode is kept in such a way that this is in the proportional to this thing, and the proportionality constant is typically 10 power 5, etc. Okay. So, that is the proportional counter. And now, a slightly better version of this proportional counter is called a multi-wire proportional counter. A typical arrangement is basically a cathode, two cathode plates and anode wires kept in a plane. So, these are the transsectional view of the cross. When you have the whole thing cut in a cross section, you can actually see the cross section of the wires, anode wires also. Okay. So, that is at the center. So, these are different anodes kept at some small distance away from each other, and cathode plates. So, cathode. Now, when a charged particle pass through this, right, when a charged particle pass through this, it produces electrons like what we discussed earlier, and then they will move towards some anode wire, and the nearest anode wire will pick up the avalanche. Similar to the earlier case, this will be. So, instead of one anode wire, there are many anode wires, and the advantage therefore is that the position of the particle can also be detected. In the earlier case, we do not know where it is coming. There was only one anode wire, and then wherever this was produced inside the detector, the same anode wire will pick. So, information about the position where the particle passed through was not available, whereas in this case we have different anode wires, and then each of these anode wires, the signal is read out separately. So, we know which of the anode wire is picking up the avalanche or the shower from the ionization or due to the ionization of the gas, and from that we will know roughly which way the particle has passed through. Okay. So, this information is an additional information that you can get. Same information you can get also from what is called a drift chamber. So, the drift chamber is is an arrangement similar to the multi-wire proportional chamber. And the difference is that in the case of multi-wire proportional chamber, you do not have any much time lag between the entry of the particle and the avalanche. So, almost immediately, so the anode wires, the potential and the anode wires are so that positions of the anode wires are so that the avalanche happens almost immediately. In the case of drift chamber, what is done is that there is an arrangement of the cathode wires, which are these are cathode wires, and anode wires, so that there is reasonable separation between the anode wires, typically a few centimeters. Okay, this is anode. Typically, a few centimeters is the distance between the anode wires, and the cathode wires are arranged so that most of the regions, excepting very near the cathode anodes, the electric field is constant. And when you see that when a particle enters, a charged particle, high energy charged particle enters this region, this detector, again the particle will ionize the gas and the electrons will move towards one of the anodes, and avalanche happens very near that anode. But since the distance between the anodes are large, usually a primary electrons produced away from any of the anodes, and it will slowly drift because the electric field is constant and low. It will slowly drift towards the anode for some time, and it takes a little while for it to attain the energy needed to have the avalanche, to create secondary ionizations or further ionizations and the avalanche. It takes a little time. So, that is the key here, and you have either at below the arrangement or above the arrangement, below the arrangement, say you have what is called a scintillator or some detectors which actually detects the presence of this particle or the time at which this particle actually goes through. So, roughly we know when the primary electron is produced. This is with the help of an additional fast detector, which is helping this drift chamber in finding the distance or the position of the particle's entry. How? So, T 0 is known when it is entering or ionizing the primary this thing, and avalanche happens at a slightly later time, say T 1. This time gap and the drift velocity of the electron produced is known from the arrangements, the voltage, the electric field applied, etc. We know the drift speed of this particle, and this information along with the time difference will actually help us calculate the position of the particle when it actually produced the primary electron, and or the other way it is basically the time of entry or the position where the particle has entered. Okay. So, time of the primary ionization is T 0 and then time of avalanche is T 1, say. So, T 1 minus T 0 the time difference and the drift velocity of the primary electron, the position of the particle can be determined. Another thing, just now when we mentioned a scintillation counter, that is another type of detector. When charged particle pass through certain materials, atoms of these materials are excited. These materials are called scintillators, and when these excited atoms de-excite, there will be luminescence. Okay. It will emit radiation, it will emit electromagnetic radiation. This is basically in the visible range, and then it is a scintillator. This particular this luminescence is called scintillation. Okay. And this luminescence is recorded using a photomultiplier arrangement. There will be a photocathode on which the scintillation falls, and that emits photoelectrons, and these photoelectrons will actually be multiplied using or with the help of diodes, and finally, the anode will pick up the increased signal, and that can be fed to a computer or reading system. And this is a scintillation counter arrangement. Another type of detector is called the Cherenkov detector. Here, this is very similar to the shock waves, mechanical shock waves generated when particles move faster than the speed of light in that medium, and then shock waves are produced, we know that. Similar to that, electromagnetic shock waves we can call it maybe. Electromagnetic waves are generated when the charged particle moves in a medium with speed larger than the speed of light in that medium, of course. And this radiation can be used to determine the presence of the particle, and there are a lot of useful things for this in connection with this Cherenkov detection, and we can detect the presence of the particle, the property of the particle, etc. from that. Another basic detector is a semiconductor detector. Okay. So, this is basically many of the ideas of these ideas that we said just now, like the proportional counter, the multi-wire proportional counter, etc., or the drift chamber, etc., can be miniaturized in solid state devices. Okay. This the advantage here is that they are small in size, and therefore, the resolutions, spatial resolution, precision with which we can make the position measurements or the energy measurements is high in the case of semiconductor detectors. One example is the silicon strip detector, which is basically a multi-wire, which is equivalent to a multi-wire counter. Okay. And here we do not have, these are solid state devices. Instead of ion electron pair production, we will have electron hole pair production. Now, coming to the modern complex detectors, we need many different type of these basic detectors, and many number of them, large number of them arranged in a detector system, which can be considered as a big detector with different small parts. So, and all these information from various different parts of this detector. So, the detector will have silicon strip detector and various other parts which actually absorbs the particle and give you information about the energy and various things. And this all information will be fed to a computer controlled system, and automatic data handling is necessary, because a huge number of, when say for example, beams are collided and the collisions happen very fast, and then you have to read out all this information very fast, and large amount of data is will be generated, and we have to have a system to handle all these things. And this whole arrangement, all of this arrangement together is basically making a complex detector which are used these days. As an example, we can think about the detectors of the LHC. So, we mentioned when we discussed the accelerators or the LHC accelerator, Large Hadron Collider, we mentioned that there are two general purpose experiments. One is called the ATLAS, which stands for a toroidal LHC apparatus, and another called compact muon solenoid. And there are two other systems also, one is ALICE and the LHC-B, but the main general purpose things are there. The ALICE is basically to handle the ion collisions, which can also happen in the same ring, same LHC system, acceleration and collision system. Instead of the proton beams, you can accelerate the ions and they collide and then give you information about various other things which are not possible in proton-proton collisions. And similarly, we have another experiment called LHC-B, which is specifically designed to understand a particular aspect of elementary particle dynamics, and a particular system which is called a B quark bound system, and there are a lot of information that we need to know, lot of details of this system that we need to know, need to understand to learn about the elementary particle dynamics. So, there is a special detector which is designed just for that purpose there. Atlas and CMS are two general purposes thing which is designed to learn about anything that is happening in a PP collision. So, a CMS detector is has many different parts, as you can see. Basically, the beam pipe is at the center along the axis of this, surrounding the two blue arrows that we have in this picture, and this is surrounded by different layers of detectors. First, we have what is called the silicon tracker. A silicon tracker is something which actually tracks the particles, detects the particles, type of the particle. If it is a charged particle, it can actually tell whether it is positive charged particle or a negative charged particle, etc., which is actually a silicon microstrip. Okay. There are many such microstrips which are arranged in these silicon trackers, and you have to provide the magnetic field to make the charged particle bend this way or one way or the other, so that we know what is the type of electric charge in it. For that there are superconducting solenoids which actually provides large magnetic fields, 4 Tesla, etc. And then further on, then you have what are called the electromagnetic calorimeters, which absorbs all the photons which come out of this collisions and all the electrons. So, the electrons, protons, photons, electrons and photons are absorbed completely in electromagnetic calorimeters or ECALs. So, they are there, and then you have what is called the hadron calorimeter, where other type of the protons or pions, etc., which are made of quarks like protons. These particles are absorbed in HCal or hadron calorimeter, and then we have the muon chambers at the end of this one, and a lot of things are there. There are different parts like forward calorimeter, which are kept along the beam slightly away from the center of this thing, so that you can get information even at small angles of detection and or angles near 180 and one near 0. This can also be picked up. Particles which are actually scattered at very small angles or very large angle in the backward direction are picked up using the forward and the backward calorimeters regions. And you have various other parts of these things which you can see, and this detector is a huge arrangement. Its total weight is 14,000 tons, and the size, overall diameter is 15 meters, and you can see the comparison with a person standing there, how huge this one is. Okay, so more about it, you can look at the details either in this picture or many such pictures and details available at CERN's website, which is mentioned here. And this is the same thing that we are in cross sectional view of this, one part of this, that is a radius of something like 7 meters is given here. So, you can see it is to scale actually to some extent. Silicon tracker is very small here, and then that actually tells you what is the type of particle, what charge is the particle having, whether it is a neutral particle which goes straight, okay, like which is mentioned here, that green dashed line inside that silicon tracker is basically a neutral particle. It does not bend. As I said, there is a large magnetic field about 4 Tesla. So, that will bend the electric charged particles somewhat visible visible bend you can see. Okay. This is a reconstruction, all these tracks are reconstructions of information that is fed to the computers. If it is a charged particle, that will bend. If it is a positively charged particle, it will bend one way. If it is a negatively charged particle, it will bend the other way around. And the blue line is a blue dash line, is photon, which actually goes straight again because it is electrically neutral, but then is fully absorbed in the electromagnetic calorimeter. Okay. Whereas, neutral hadron like pion etc., we will come to what are the different hadrons that we know of at a later stage, but they are basically made particles like protons or particles which are made of quarks. See, if there are neutral protons, neutral hadrons, and the neutral hadrons are absorbed, go straight in the silicon tracker and absorbed in the hadron calorimeter. Whereas, charged hadrons, the green solid line say, they are bent and go past the electromagnetic calorimeter and get absorbed in the hadron calorimeter. Whereas, the electrons which are red lines here, they bend in the they are bent in the silicon tracker and get absorbed completely in the electromagnetic calorimeter. The other type of particle generally produced are the muons. Okay. Muons go past the electromagnetic calorimeter. They are slightly bent, and they cannot be bent too much because the energy is quite high, and the radius of curvature will be very large in that case. And they go past the hadron calorimeter as well, and they leave their traces in the outer part of the detector, which is called the muon chamber. Okay. So, there are different chambers actually. So, there are different sets of these muon chambers, and each of these will detect the presence of the muon passing through that. And there is another magnetic field which is kept there, so that will actually bend the magnetic field, the muons for again, and then we can make sure that it is actually a charged particle, muon charged particle, which is moving through that in that way. And these muon chambers there are separated by ion sheets which also absorb these muons quite a bit. Okay. So, this is basically the general setup there. Okay. One thing I should say, in this picture the interaction point is basically at the vertex of the silicon detector, silicon tracker, and the beam is passing perpendicular to this thing. Okay. So, that is how the geometry is here, and we are seeing a cross sectional view in this case.